Hello everyone, I'm Benjamin Barton and I'm going to talk to you about the technical details of the Scottish Shelf Water Reanalysis service. So this is going to be a bit about the model setup and forcing. So the Scottish Shelf Water Reanalysis service is based on an earlier version of the model, the Scottish Shelf model, and this takes advantage of FVCOM, which is an unstructured model and has a dynamic resolution that goes from 10 kilometers near the Atlantic boundary to 500 meters in coastal areas. So this provides the aim of the model, the project, is to provide a 25-year physical reanalysis of the Northwest European shelf, going from 1993 to 2017, and this will give improved temperature and salinity compared to the Scottish Shelf model. So what I'm going to run through today is the upgrades to the bathymetry, tell you about additional rivers that we've put in. We've opened up the Baltic boundary and added in sea surface temperature assimilation. I'm going to tell you about running FVCOM, some changes we've made to the original setup in version 1.1, and then some validation of the model output. So first of all, the bathymetry upgrade that we've done. This was needed from the Scottish Shelf model because the original Scottish Shelf model was referenced to lowest astronomical tide. So we've switched over to using the NEMO Atlantic margin model AMM15 bathymetry dataset, and this is referenced to mean sea level. So we can see the difference between the old SSM model bathymetry and the new SSW-RS bathymetry. So they're interpolated onto the same grid here, and I guess most of the difference is in deeper regions off the shelf that we're not too worried about. And then I guess there's a slight difference over most of the shelf where we've got the difference between the reference level. And then we can then see how much difference that makes to the model sea surface height. So this is just two example runs over 5 days that we've then taken the difference between the sea surface height for the two cases of the two bathymetries, and then we're looking at the standard deviation here between the difference between the two of the sea surface height. So generally in coastal areas we've got a difference which can be half a metre or more, showing that it was worthwhile updating the bathymetry for that. Another change to bathymetry is that we want to adapt the bathymetry for the river nodes. So we've defined a region around each river node of the two connected additional connected river nodes. This defines the sort of estuarine area, and all these nodes are then deepened by 5 meters or more, depending on the river flux into that node. And this on the right just shows a map of where we've got deepened river nodes around Scotland. So the yellow node points here are the adjusted nodes. Changes to the river dataset. So we've updated to the eHype Reanalysis river dataset, which has interannual variability. It has coverage over all of the Northwest European shelf, and as well as river flux, it also has river temperature. One of the downsides of this eHype dataset compared to the CEH grid-to-grid model rivers that were in the Scottish Shelf model is that it's lower resolution spatially in Scotland and Northern Ireland. So how can we get the high spatial resolution and interannual variability here? The solution we've come up with is to match each of the grid-to-grid rivers to a eHype river, and that matching is done based on the distance between the two nodes, the 2 points, as well as the mean volume flux and the regression value between the climatology of eHype and the climatology grid-to-grid data. On the right, just some example in Scotland. So we've got the more numerous grid-to-grid nodes for the rivers around the coast, and then an example of connecting the or matching the Clyde grid-to-grid node to a eHype node. So once the rivers are matched up, I calculate a intercept-free regression between the G2G river climatology and the eHype river flux climatology. So the blue here is the G2G, yellow is the eHype climatology that's been calculated, and then the red line is the intercept-free regression model that we then use to adjust the eHype data to the level found in the G2G data. And the reason we use the intercept-free regression method is because we don't want negative volume fluxes in the river. So then once we calculated the regression model, this can be applied to the eHype data, the interannual variability, so that each G2G point then has interannual variability. So each G2G river can be matched to each eHype river can be matched to multiple G2G rivers, since they're more numerous, higher resolution G2G river nodes. But that means that each G2G will have its own flux. So then we also add the rest of the eHype data set in the Northwest European Shelf. So here the blue is the high resolution G2G points and the original Scottish Shelf model, and these are carried over to the SSW-RS as well. And then we have additional river nodes in green that are added in outside of Scotland and Northern Ireland. So all the river nodes have interannual variability now. The Baltic boundary, and I guess there's also a change to the Atlantic boundary. So the Atlantic was in the Scottish Shelf model, the original version, and here we've also opened up the Baltic boundary here with these green nodes. The Atlantic boundary needs interannual variability, which we take from the 7 kilometre NEMO model AMM7. So for sea surface height, we get the daily residual and add in TPX09 harmonic tides to that across all the nodes. Same for the velocity, we get the residual from the AMM7 and add in TPX09 harmonic tides. And then temperature salinity just come direct from the model. And then the Baltic boundary, we use a different model, which is the 4 kilometre Baltic NEMO model. And that covers this region as well as some of the North Sea. And the reason for using two separate NEMO models here is because the MM7 doesn't cover this boundary so well. In the Baltic NEMO model, we want to take the sea surface height, and that already includes tides at an hourly interval, and then velocity is taken at daily interval from the NEMO model and has the TPX09 tides added in. And then temperature and salinity, just comes direct from the NEMO model output, so that's applied to that boundary. How much difference does it make? So what we're looking at here is the UMV velocities for test case of 1 month run, where we have the Baltic boundary open and the Baltic boundary closed. And basically what we see is the difference between the red and the brown, and the difference between the blue and the green, that there is a difference in the velocities through near the Baltic boundary here, this example location. And also there's a bigger difference in the salinity for the cases of Baltic open and Baltic closed. So yes, it's worthwhile opening up that boundary. Here's a snapshot example of surface temperature from the model and salinity, so that we can see that we've got fresh water coming in from the Baltic there, and it also nicely shows that we've got lots of fresh water coming from coastal regions from the river data set. And then this is just an example of the velocities, showing one tidal cycle, 24 hours, of a depth average velocity, and they can see that there's velocity coming through the Baltic boundary, as well as tides circulating around the northwest European shelf. So another upgrade that we've done to the model is to have sea surface temperature simulation. And the dataset that we've used here is the Odyssey sea surface temperature, which is a satellite-only product, so it doesn't have in situ data as well. And it's a nighttime sub-skin temperature. And the method that we've used for simulating this data is the nudging method, which uses weighting to nudge the model based on the distance between the observation and the model, and the time between the observation and the model, and the temperature difference between the two, to adjust the model to the correct temperature, at least the satellite temperature. And that's simulated at midnight, over for a 3-hour period between 10:30 and 1:30 in the morning. So the difference that we then, the model is still allowed to evolve freely, even though it's being nudged by the sea surface temperature. So that can be seen here just as an example over the summer, where there's tidal and daily variability in the model compared to the blue satellite. Although the model is showing it's following a lot of the main variability and spatial patterns in the satellite data, so we're getting fronts and things in the right place. Also is an example of two model run examples when we've got sea surface temperature simulation, and then an example in yellow here without simulation. So there's a difference in the temperature. In the winter it's getting cooler when we have sea surface temperature simulation. And it's also affecting the salinity a bit. This example location in the Baltic, where I think the fronts are constraining fresh water in different ways when we have the sea surface temperature simulation affecting the salinity. Running FVCOM, right, so that's one thing I missed out so far is the atmospheric data that we're using to force the model to give it interannual variability, and that comes from the European Centre for Medium Range Forecasts, ERA5 dataset, which covers our run period from 1993 to 2017. I guess some facts about the grid is that it's got 267,000 nodes and 521,000 elements. The vertical levels are sigma, terrain following, and we've got 20 depth levels that are distributed evenly over the water column. The SSW-RS is run in parallel on high-performance computing services, and it is running on 8 nodes over 256 processor cores. The performance we're getting is 35 minutes per day of model output. The changes that we've got, that we've decided to make to the model in version 1.1. So this was in 1993 and 1994. We decided that there were a few things that could be improved slightly. So from December 1994 onwards, we've made changes to the Atlantic boundary sea surface height, and this was a correction to the mean dynamic topography, which we'd overcorrected before. So this is how it should be. This is the time period when we hadn't corrected it. So this is comparing AMM7 and the Baltic NEMO model. So they should be have similar sea surface height rather than these time periods when there is a bit of a difference in the sea surface height. So that's been corrected for 1995 onwards, so this whole time period onwards is now correct. And then we also found that the rivers were being unstable at times when there was zero river flux. The temperature in the eHype dataset of the river temperature was fluctuating and causing problems. So to fix this, the river fluxes have been smoothed with a 3-day running mean to smooth out big, changes in the flux, and then zero flux times in the rivers is set to 0.01 cubic meters per second, just so it's not going to zero. And then at these times also setting the river temperature to climatological river temperature for that river. The rivers, we've also set a lower threshold of 1,000 cubic meters per second for the maximum when rivers are split over a larger number of nodes, just to distribute the fresh water over a wider area. And this means we get slightly more river nodes, and that after 2005. And there's also some slight changes to the bathymetry, making the estuarine areas slightly deeper after that as well, just to accommodate the freshwater flux. Just to show that these changes have made a small difference to the model run. So AMM7 here we're using as a reference for the salinity, and this is an example in the Baltic, near the Baltic boundary again, the same location. And version 1 without these changes is shown in yellow, and version 1.1 is shown in blue. So yeah, that basically we're getting a bit more fresh water coming through the Baltic, having made these changes. and yeah, I think that's mostly due to the sea surface height change that we made. I mean, before 1995 in 2003 2004, the model is still running fine. It's just a slight bit of improvement after that. So validation, we've done some validation on the model using the Cora data set available from CMEMS. This is a hydrographic profile data set, and I've selected profiles on the Northwest European shelf. Here showing ones that are less than 200 meters deep, and there are 4,000 temperature profiles here over this time period from 1995 to 2000. In black we've got the observation profiles, which are then matched in time and space to the correct node in the model, which is shown in red, and that's been reflected in 0 degrees, just so that the two aren't laying on top of each other, and you can compare and see that a lot of the variability and the depth of the profiles and temperature is modelled very well. Also the salinity. So this is showing 1,000 salinity profiles over the same area, and so the model data here has been reflected in 35.5 degrees, 35.5 salinity. Again, model in red and observations in black, and yeah, again that's showing that there's a variability in the salinity that's been captured by the model. And we can show spatial maps as climatologies here, showing the difference or the similarity between the observations and the model. So profiles are shown in the top plot, averaged over the upper 20 meters of the water column, and the same is shown for the model in the lower plots for spring, summer, autumn, and winter. And yeah, basically they're very similar, perhaps to be expected, considering we're assimilating sea surface temperature in the model. But yeah, the differences are very subtle. Salinity now, same again, climatology plots of the profiles averaged in the top 20 meters for the observations and the model in the lower panels. So that again, it's actually doing a really good job of simulating the salinity, especially considering here we don't have salinity assimilation. So this is just based on boundaries and river fluxes, and yeah, it's got showing good spatial patterns. I think the model is slightly saltier in the North Sea, but it's quite subtle. I'm pretty happy with that. And then the sea surface height. So this is comparing satellite TPXO. Satellite Topex Poseidon data from 1995, and here we've got model on the X and observation satellite data on the Y. So there's good agreement between the two. This is including the variability from tides, giving an R value of 0.5. On the right is the continuous ranked probability score for comparing the observation satellite data point with a ensemble of the surrounding model points in space, just to avoid biases from small scale variability. So a lower score here is better, and it's basically showing that a lot of the model region is comparing well to the satellite data, and I think some of the more coastal regions are likely noise in the satellite data. These are the data sets that have been used from Siemens and other sources in forcing and validating the model. So open boundaries, atmosphere, rivers, tides, sea surface temperature, and then some validation data sets. And that's about it from me. I'm Ben Barton, and thank you for listening to my talk and learning about the Scottish Shelf Water Reanalysis Service. And I'll leave you with this little comic that I like from XKCD. Thanks.